We're going to be talking about the ELPRO 415U-1 radio system. And again, just as a reminder, we are recording this session, so if I can ask you to please mute your microphones. Now, here's where the 415U-1 falls in the overall portfolio. It is a remote I/O radio system. So the 415U-1 has two analog inputs for 4 to 20 milliamp inputs. It has 4 DIO, so they can function as digital inputs or digital outputs. As well, it's got an SDI12 interface on the radio system as well. The 415U-1 distinguishes itself from the 415U-2 by its enclosure. The enclosure is rated IP66, so it can be left outdoors, unprotected from the elements there. We'll jump into greater detail on the product in just a minute, but this is just a quick breakdown of the ELPRO portfolio. The radios across the top row, they are remote I/O devices, so they have 4 to 20 milliamp inputs and outputs and discrete inputs and outputs. And the 415 radios, anything that starts with a 4 is a 450 megahertz radio system. And it would be compatible with any other 450 megahertz radio system. For example, the 415U-2, the 415U-E, and the 415U-1 are all compatible over the air. So we can have a 415U-1 at a remote site. We could have a 415U-2 at a different site that has an electrical enclosure suitable for the radio housing. And then back in the control room, we might have the 415U-E, which has an Ethernet and serial interfaces for Modbus communications to communicate with a SCADA system. Now, just to give you a quick overview of what we do here at ELPRO, the remote I/O series of radios all have 4 to 20 milliamp inputs and outputs. The gateway type radios have the ability to communicate using a protocol such as Modbus RTU, Modbus TCP, or Allen Bradley's Ethernet IP protocol. Then we have a different class of radios called our Ethernet pass-through modems. Essentially, whatever you put into the Ethernet port of one radio comes out the Ethernet port of the opposite radio. And lastly, we have serial and cellular type modems. So I'd just like to quickly review the product line just to give you an overview of what we do for a living here at ELPRO. And again, today's focus is the 415U-1 450 megahertz licensed radio. Okay, the Condor series was a new generation of radios that we developed approximately 3 to 4 years ago, and it consists of this generation of devices here. As long as these radios are on the same frequency, they can all communicate with one another. So in this case, our 415U-1 can communicate with the 415U-E as well as the 415U-2. Now, I'd like to just highlight the differences between these the 415 radios. The 415U-2 has 4 analog inputs, 2 analog outputs, and then 8 DIO on the radio system. It is very similar to the 415U-E, except the 415U-E has none of that I/O. It just has one DIO point on the terminal block. The 415U-2 can do everything that the 415U-E is capable of, as well as has this additional I/O. So this would sort of be a base model, I suppose. And then we would bump up to this unit here, which has the improved flexibility of additional I/O built into the terminal block. Then we have the 415U-1, which has 2 analog inputs and then 4 DIO. But the main difference is it is housed in this IP66 weather-tight electrical enclosure. We've got a couple of glands across the bottom for getting our cables into the enclosure. And the antenna port is a Type N connector on the top of the radio system. In the future, we will be releasing a version of the 415 IoT. This will have a variety of different possible radios inside of it. It could have a cellular radio, it could have a 900 megahertz radio, and in some cases, it will have both. It will have more than one type of radio system to act as a gateway for other 900 or 450 megahertz radios. So the 415 IoT is something we expect to be releasing around the end of this year. Yeah, it should be a very interesting product when it comes out. We can certainly vision quite a number of applications for that device. Now, just to quickly cover the 215U-2, it's going to be very similar to the 415U-2. The main difference is the frequency of operation. This is a 2.4 gigahertz radio, and it uses the 802.11 BGN wireless protocols. Okay, so just to be clear, a network using the 415U-1 can also consist of 415U-Es or 415U-2s as needed. These are all compatible over the air. Okay, now with the 415 series, we're talking about very long distance wireless communications. And with a 450 megahertz radio, the maximum range is typically going to be about 50 miles. So we can get some incredible distances out of this particular frequency band. And that is because the FCC permits up to 5 watts of transmit power compared to just 1 watt at 900 megahertz. So we're going to be able to go some pretty significant, some pretty substantial distances. And they're great for SCADA applications, for doing process control, for monitoring remote sites that don't have power. And, whoop, I'm sorry, it looks like my slideshow seemed to click away for just a minute. I apologize there. But designed for, as I was mentioning, designed for very long distances, much greater distances than can be accomplished with 900 megahertz. Or even compared to 2.4 gigahertz, we can go drastically farther with 450 megahertz. So just as a rule of thumb is the lower the frequency, the greater the range of the radio system, the better the object penetration ability. So we can shoot through more houses and trees and that sort of thing. So that's why we would choose a 450 megahertz radio system, would be to be able to get that additional distance out of it. And of course, here at ELPRO, we have the ability to design SCADA networks. And this is just one example right here of picking up a whole bunch of data points around a university campus. And we, couple of the remote sites were a bit distant. So we set up a repeater site for some of the remotes. But when we do this, we have the ability to plot what the profile is going to look like. And with this software program, we can estimate what the received signal strength is going to be. That's one of the key things. Some other interesting information we can get from this path loss software modeling program is it will calculate the distance, of course. And we can enter in all of our parameters, such in this case, it was a 1 watt radio operating at 900 megahertz. And the antennas, we can change the antenna height to see if we can improve the signal to clear these trees. And the software program also allows you to download the terrain files for the area in question, which are generated by the U.S. Geological Service, and they show us what sort of foliage is likely in the path. So tremendous amounts of information can be gained from doing a software model or a path loss study of the sites in question. Now, the other one of the biggest questions that always pops up with 450 megahertz radios, or in fact, this happens with a lot of different types of radios, is what is the distance? How far can I go? And how high do I have to have my antennas above ground? As you can see from this chart, as the distance gets greater and greater, the antennas need to be mounted higher and higher above ground. And this is due to something called the Fresnel zone clearance. So that's a subject for another session. But for now, the important thing to note is that as distances get greater and greater, the antennas have to be higher and higher above ground. So you may want to factor that into your design consideration to make sure that you do have some sort of structure you can mount these antennas on if you are shooting these very long distances here. Now, when I say obstructions here, at 2,000 feet, we can tolerate very, very dense obstructions. We can shoot through houses, trees, even a little bit of land. As soon as we get up to about 5,000 feet, roughly 1 mile, light obstructions are what we can tolerate. Same with up to about, say, 2,000 miles, or even, 2 miles, not 2,000 miles. That was 2 miles there. We can tolerate some light obstructions. Then once we get up to 3 miles, anything beyond about 3 miles, that's where we should have line of sight. So where you see LOS, that stands for line of sight. And these antennas, these are small omni antennas. Then they get up to a bigger omni antenna. Then we switch to Yagi antennas because they have higher gain and we can get longer distances out of it. So the antennas, the gain of the antenna system increases, and the antennas also get physically larger and larger as we get to higher gain, longer distance antennas. So this will give you a ballpark as to what sort of distances we can achieve. Now, keep in mind, we do have some customers in the Gulf of Mexico, oil and gas customers, and they recently designed a system using our 450 megahertz radios, and they were able to shoot about 45 miles. And that was going from a ship to an offshore oil rig. So we do have customers that do push these radios right to the limits, and they will perform, when you have suitable antenna height and suitable antenna gain. Okay, now we also have a demo kit, which is swappable so that we can insert 450 megahertz radios into the demo kit. Then we can have a look at the display on the HMI, and we can see what the received signal strength is. And typically, this is what you'll end up doing: is you'll have somebody on one end holding up an antenna. And what this is actually a flagpole, a trailer hitch flagpole mount. And one of our distributors just modified it. Instead of a flag, we of course have an antenna at the top, and it has a little base that rests on the ground, hooks onto the hitch of the trailer. And this allows you to hook up a higher gain antenna onto your demo kit, so that you can test 450 megahertz radio links. So that's how we figure out what sort of distance we can get with these radios. Is initially we can look at a path loss software study, and that creates a model of what the terrain is going to look like. And then if we were still uncertain, or we really wanted to just double check it, then we would go out with the demo kit and test it with a pair of these radios in the actual environment with the actual trees. Keep in mind that a software model is just that. It is a model, and that a test in the real world with the actual radios themselves that we're going to use, that is going to give you a more accurate result than a software model will. Okay, so once we've figured out our full our radio links and making sure that we can connect to all of our different remote sites, and we'll have figured out which antennas we need to do to install at each remote site, then we can come up with our full hardware offering.
And the hardware offering for any radio system will always consist of a minimum of 4 items, and that is the antenna, some coaxial cable to allow you to mount the antenna up high, a lightning arrestor, and the radio transceiver itself. The rest of the items we obviously have to have. Well, we need the power for the radio system. We might have some surge diverters on the radio system as well. But in a nutshell, it's 4 items as a minimum: the antenna, the cable, the arrestor, and the radio system itself. Okay, just as a reminder, I can hear a couple of voices in the background. We are recording today's session. So again, if I can just remind you to please mute your microphones. Now, one of the other things is a license for 450 megahertz, or for that matter, 150 megahertz. While I refer to the 415U-2 as or the 415U-1 as a 450 megahertz radio, we also build it in a 150 megahertz license band. And if you think we can get 50 miles at 450, well, at 150 megahertz, we can get up to 70 miles of distance out of these radio systems. So again, it's just the lower the frequency, the greater the distance, the better the object penetration. But again, we're dealing with a licensed radio. So we have to make sure, if we're in the US, we have to make sure we get an FCC license. And here's the process for how you get it. The first thing is you have to hire a frequency coordinator, such as a company we deal with called Business Radio Licensing in California. And they can get a license for anywhere in the US. Now, what you do is you have to fill out a form. The end customer or the frequency owner is the one that has to fill it out, not the distributor of our equipment. The end user has to fill out the form. They'll ask for GPS coordinates of all the locations. They'll ask you a couple other basic questions. Which are the masters? Which are the remote sites? Are you using Omni or Yagi antennas at each site? And this will help them figure out the radiation pattern and how far the signals will spread. And they'll ask you, what's your maximum antenna height? So not for every antenna, but, are the antennas less than 40 feet? Are they less than 30 feet? That sort of thing. The next step is the cost is typically about $1,000, maybe $1,200, a one-time fee to the frequency coordinator. The process seems to take roughly 2 months. That's been our experience, seems to take them a couple of months to assess the sites. And once you have your FCC license, you can go ahead and power these radios on. So this is how we get an FCC license in the US. It's really not a very complicated process. As we mentioned, companies like this, there's lots of other competitors to this type of company, but there are companies out there that specialize in obtaining licenses for licensed radio systems in the US. So if you have any questions at all, prior to applying for a license, or you want to know how difficult or how long it is, just pick up the phone and give these guys a call. They're really great. They're very helpful. They'll answer any question you may have regarding a SCADA application. Here's what the form looks like. They're going to ask you, what sort of organization are you? What kind of, is it a new license or modifying the existing, the frequency band you're looking at, and this sort of thing here. And if you have any questions like, splits for VHF repeater and stuff like that, just give them a call and they'll tell you exactly what they're referring to here. Okay, so that's it. I mean, that's just one page. Of course, they'll ask you for the GPS coordinates as well. When they're finished, they'll give you one of these certifications. This will come straight from the FCC. And they'll tell you things like when it's effective, when it expires. And as you can see, typically you're given a 10-year license time frame. And they'll give you a couple of locations that you're referring to. And here we go. Location 3 is just the area of operation is within a 16-kilometer radius of fixed location 1. So in this case, they're not really specifying any specific exact sites where you can install the radios. They're just saying within a radius
of this #1 site right here, 16 kilometers around there, and you're good to go. Then they'll tell you what your frequency here is. And as you can see, this is a license for 2 separate frequencies. And your emissions designator, your transmit power, and your ERP. The ERP is a combination of the transmit power expressed in decibels, plus the antenna gain minus your coax cable losses. So really, it's the net gain that you would see at the actual antenna itself. So here we go. Now you can search on the FCC website. You can pull up this license for any customer anywhere in the US. So this is considered public information. Okay, now that we figure out how far the radios will go, how to get our FCC license, the next is we need to talk about some specifics about the 415 U-1. Now it's designed in Brisbane, Australia by ELPRO's RF design development team. We've been designing radio systems for over 35 years now, and we have designed all sorts of different radios, and they're all specific to SCADA or process control applications. So none of these radios are designed to do voice communications. They all do machine-to-machine communications. So that's where we're picking up signals from 4 to 20 milliamp level sensors or pressure transmitters or temperature transmitters, and we're radioing them some distance back to a control room where that information is monitored and actions taken based on those inputs. So what it is self-contained battery or solar power supply unit integrated into this IP66 housing that we have developed here. Now, this is an aluminum housing, so it does look heavy. It is quite robust, but made out of aluminum, it doesn't weigh a ton. So it's pretty easy to mount on a pole. And, just to give you an idea, the unit's about, I'd say it's about 8 inches, 8 or 9 inches tall. And we're looking at about maybe 6 inches in width and about, I'd say about 3 inches in depth. So the device is pretty compact. It's certainly not a large enclosure, so it's easy to mount and easy to handle and deal with. The lid opens. We've got some hinges on the left-hand side. We've got a bunch of screws across the front here that tighten and secure a gasket to maintain that IP66 rating. And then our cable glands are across the bottom here. And we provide with 2 optional cable glands and then just plain plugs. So if you can get all your cables into the one housing, you would just remove these 2 cable glands and insert the plugs that we provide. Now we have a built-in solar regulator for the 415 U-1. As well, we have a battery location inside of this housing. The battery is a rechargeable lithium battery. And I've got another slide that shows you a battery life calculation. But what we do is we hook that internal battery, or we hook this module up to a solar panel. And keep in mind, it must be a 12-volt solar panel. We're not compatible with the 24-volt solar panels, so it must be a 12-volt output solar panel. And the radio has the charge regulator built right in for the solar panel. So during the daytime, the solar charges the battery and powers the radio system. At nighttime, the internal battery takes over and powers the radio system. Okay, we've got DNP3 support inside of the unit here. We also have the ability of doing Modbus inside the radio as well. And I'll show you what the junction box inside the unit looks like. We've got a couple of pictures as well to show you how easy it is and how quick it is to wire. And then in terms of mounting, this is typically either going to be a flat panel mount, with some screws drilled right through these holes at the bottom here on the bottom of the enclosure, or we're going to have some pipe strapping, and it's pipe mount. We provide a little bracket there to get you onto a 2-inch pole mount there. And here we go. 2 analog inputs, then 4 discrete or pulsed inputs. In fact, they're DIO, so they can be digital inputs or digital outputs. And then we have this SDI12 and Modbus gateway interface for smart devices that have a Modbus output to them. And as I mentioned earlier, the 415U-1 compatible with all of the other Condor radios, as long as the frequency is the same. If it's a 450 megahertz Condor radio, it's compatible with the 415U-1 over the air. Okay, so here's the key features. Going into a little more detail, we have a 150, a 450 megahertz, and then a 900 megahertz licensed version will be coming out in the future. Now, 900 megahertz can be licensed or license-free. This is the licensed version that I'm referring to. The license-free portion of the spectrum is from 902 to 928 megahertz. The licensed portion of the spectrum is from 930 to 960 megahertz. So again, with the license, it's the same as with the 450. You have to apply to the FCC to get that license. And then once you have that license, you are the exclusive owner of that frequency in your area. Nobody else would be permitted to use a radio system on the same frequency in your geographic area. Okay. Analog inputs and outputs. We've got the 2 analog 4 to 20 milliamp inputs. These are compatible with both 2 and 4 wire type devices. So the radio can provide a 24 volt output for powering a 2-wire 4 to 20 milliamp transmitter. We also have these analog set points, and I'm going to chat about them in just a minute, but what we do is we can monitor an analog input, and we can say, hey, when that analog input drops down to a value of, say, 5 milliamps, I want to turn on a digital output to turn on a pump, for example, to fill a tank. And I'll show you how that works in a couple of minutes here. Now we've got in the SDI12 interface, up to 62 sensors can be connected to a single radio, and we provide a 12 volt DC switch supply for these SDI sensors. Then we have outputs. We have 4 discrete outputs, and they are latched outputs. So once you turn them on, they remain on until you turn them off. And the radio maintains the status of these outputs regardless of whether it is in sleep mode or whether it's actively powered on and taking samples. And we're thinking in the future we might add a couple of extra I/O or make it available via terminal block. And we've got a couple of other features that we're going to be adding to it. In the future, we'll be adding Bluetooth capability to it. And that'll be for configuration or diagnostic, so you wouldn't need to directly plug into the radio. You can connect to it via Bluetooth to a tablet, for example. In terms of encryption, AES 256-bit encryption today is considered unhackable with the processing today's computing power. So even if you had a supercomputer, I saw one fellow do a calculation. I think it was expressed in the number of years it would require to hack this AES encryption. And let's just say 5 years down the road, processing ability does speed up, and maybe somebody does find a fault with the AES encryption. We have firmware upgrades that will upgrade the security. So as new encryption techniques come out and we are able to integrate them into our products, we will make that available via a firmware update. And that's how we future-proof this product. to make sure that it never goes obsolete or loses functionality. Okay, we have Modbus RTU gateway for smart devices in the field. So you can just wire up your RS-45 twisted pair from a Modbus instrument directly into the radio. And we can now transfer that type of data as well as 4 to 20 milliamp and discrete I/O points. Okay. And yeah, we've got lots of other products, all Condor products that will communicate with this particular radio system. We've got a bunch of different power options. We can have an external power source of, this would be considered a nominal 24-volt power source, but it can vary from 17 to 30 volts DC. Then we can have a solar panel. I should say there's a correction here. There is no limit to the power rating of the solar panel. The only limit is that the charge regulator will send a maximum of 2 amps of current into the battery during charging. So if you're way up north and you need a big solar panel, no problem. You can fit a 50-watt solar panel on this radio if you like. If you're down south and you got lots of sun, you can drop that down to 30 watts or something of that sort. Okay, and then we offer a couple of different batteries. The most popular one is the internal rechargeable lithium battery. This LFP is the chemical formula for it. But we also offer a non-rechargeable battery. And so that would be ideal if you've got, say, a reservoir, and the reservoir has no power, and it's out in the middle of nowhere. Up here in British Columbia, there's a ton of these hydroelectric reservoirs, and a lot of them are very, very remote mountainous sites. There's no power at a lot of these locations, and they want to monitor what these levels are upstream of the dam so that they can control the water flows for a variety of purposes, obviously electrical generation, but there might also be recreational users of that same body of water. So we've got a bunch of different power options here for remote sites. And again, the radio really is designed to be left out on its own in sites where there is no power, there's no infrastructure, that sort of thing. This is really what this guy was designed for. It's a standalone device there. Whoop, sorry guys, my computer seemed to get a mind of its own, or maybe that was me with the mouse click, I'm not really sure, but let's just carry on nonetheless. Here we go. This is showing the battery life solar panel size calculator that we've developed for the 415U-1. And it's an Excel spreadsheet. So what we do is we just enter in all the parameters. You know, we got some pull down menus. You select your transmit power and what modulation scheme you're going to use, your over-the-air data rate, how many 4 to 20 milliamp sensors you've got, how many discrete sensors you've got, and then you set up your sampling time. Now with these radio systems, if we are providing power for the 4 to 20 milliamp loop, we want to power on the sensor for a period of time to let it warm up and let the reading stabilize. So in this case, we're just giving this sensor 4 seconds for the reading to stabilize. So the radio powers the 4 to 20 loop. The sensor, it takes warms it up for 4 seconds, and then it takes a sample. And in this case, we're going to be sampling that guy about every 10 minutes or so. Okay. Then just showing this one right here. We've set this guy up so that it's going to update every 180 minutes if none of the discrete values change state. We're expecting 3 event-driven events per day. And that brings us down to this calculation right here. If we assume just 4 hours of sunlight, very conservative, but 4 hours of sunlight for a solar panel,
We estimate we would need a 20-watt solar panel for this if we have just 4 hours of sun, and we would get about 8.4 months of power out of the internal battery. And this is with our rechargeable internal lithium battery. We would estimate we would get this lifespan out of it before we had to recharge or replace it. So again, as you can see, very low power device, and this allows you to calculate exactly how long that battery is going to last and how big that solar panel needs to be. Okay, so here's one typical layout here. We can set up a unit to act as a repeater for these remote radios at different remote sites. Now, keep in mind, if we are asking the radio to act as a repeater, power consumption is going to be a little bit higher. So we'd want to bump up the size of that solar panel to make sure that we've got enough juice so that we can accurately relay the information from all of these remote radios. And here we go. So these are remote sites, remote 415U2s going to a repeater 415U2. And of course, you can have some 4 to 20 milliamp signals going into this radio, so it can function as a remote site and as a repeater for these other locations. And then, of course, we shoot all this data back to the control room radio, where we would use either the 415U-2 or the 415U-E. And then these radios are capable of Modbus as well as DNP3 protocol. So we connect that to our SCADA system, and we can control everything remotely via radio system. Okay, we can also set things up a little differently. We can use the 415U-2 as a repeater site. So there is a tremendous amount of flexibility in the layout of these radio systems. Whether we use the 415U-2, 415U-2 or the 415U-1 would just depend on the electrical enclosure available. We had an enclosure available. We can use the 415U-2. If there is no enclosure, then we can use the 415U-1. So multiple repeaters can be set up with this radio system. Okay. Now, what we do is most of the time, the traffic is event driven. So what we do is we monitor the 4 to 20 milliamp inputs. So the radio will wake up. Let's say, for example, it wakes up every 10 minutes. It powers on the 4 to 20 milliamp loop. It looks to see if there has been a change since the last time it was powered on. If the 4 to 20 milliamp signal going into this remote radio system has not changed, then the radio does not transmit anything. Then we have just our default update times, and these function as more of a communications check or just a confirmation so that the SCADA system in the control room knows that this remote site is still alive and still has power. So we set our update times maybe once per hour, once every 2 hours, something like that, making sure we don't consume too much power and have to get a really big solar panel or that sort of thing on the radio system. And the discrete inputs are monitored continuously. So because it requires extremely little power to monitor the status of a discrete input, we monitor these discrete inputs continuously. And if any discrete input changes state, that value is then radioed immediately to this repeater and then back to the control room. So the response time on discrete inputs is virtually instantaneous. The response time on analog inputs, well, that's a little more complicated because we have to power up the sensor, we have to take a reading, and we have to send that across. So it consumes a little bit more power. But we do have that sample time every 10 minutes or so. That's when the radio is going to power on the loop, take a reading, and see if there was any change. And if there was, go ahead and transmit that over the air.
So that's generally how we work. Now, we use access point and client configuration for these radio networks. The access points control the flow of all RF traffic and determine which clients will link to them. So the master radio is going to be the access point radio. And the master radio stores all this data in registers in Modbus format here. So then we can come and read this using Modbus TCP or Modbus RTU. Okay, now I took a couple of pictures of the inside of the electrical enclosure. Give you an idea as to how the unit is wired up. We have a couple of connections. You'll notice right off the bat, we've got a USB-B connection, and this is for configuring the device. Then we have a USB-A connection device, and this is for firmware upgrades. Firmware upgrades are really, really simple. All you do is you load the firmware onto a USB stick, stick it in the slot here, and power on the radio, and that's it. One of the updates that we are planning in the future is the ability to push out firmware updates over the air to all radios simultaneously. So that's something that'll make firmware updates super simple. You just plug into the master radio and you set it up for a firmware update, download the firmware file once, and now it will send that over the air to all remote sites and upgrade the firmware on all remote radios simultaneously. That's a feature that is coming in the future. We expect that approximately Q4. And as we add features to the 415, it's all upgradable via firmware. So if we talk about something that's has not come out when you receive your radio, and 6 months later we add that feature, you can access that feature through a firmware upgrade. Okay, so
Brian?
Here we have our power supply connections. We have the battery and ground terminals are located on the right-hand side. So this is where we would connect if we had a 12-volt power supply going to the radio instead of using its internal battery. If we had a 24-volt power supply coming into the radio, we would connect it between the ground and the solar input. So that is between pins 2 and 3. And lastly, we do have the option of a heater if you need it, if you're way up north and we decide we need to heat the enclosure just a tiny fractional amount, just to make sure the battery doesn't get too cold and lose its capacity. So we also have that capability, and this would only be used in extreme cases. So we're talking Arctic Circle is when we would actually need to use that heater. Okay, this is our serial port connection for doing Modbus communications. And then we also have the DIO across the bottom. So these are digital inputs or digital outputs. And then we have an LED next to each one, so you can see what the status is very easily. And then we have our 4 to 20 milliamp inputs and outputs, as well as our RS-45 communications and our SDI-12 input. So by the way, these analog inputs, they are differential inputs, which means that they can be wired at any location in your 4 to 20 milliamp loop. So it gives you just a little extra flexibility in wiring there. Okay, so that's covered. We covered the wiring. Now we'll look at the front panel LED functions. Obviously, we have our power and OK, and it just flashes once every 10 seconds in normal operation. Then we have our TX and RX LEDs, and they flicker whenever sending or receiving. And the RX LED dual color
So flashes green when we have a strong signal, red when we are receiving a weak signal. And this one turns on whenever we're making a sample from a 420 milliamp or an SDI input here. And we can also do a test transmission. So, for example, if we want to make sure that the control room is receiving everything and we're standing out at one of those remote sites, we can just push this button and the radio will go ahead and transmit the values of all of its inputs to the control room. And then we can, if you're talking to a fellow on the control room by phone, you can just say, did you get all those values? And as this forces the radio to transmit all that information. Okay. As an option, we can also turn these LEDs off if we're at a site where we don't want to attract attention, or having flashing LEDs. If that might attract vandalism, we can turn those LEDs off altogether. Okay. So I think I've pretty much covered this one here. But it does just sort of label all the inputs a little more thoroughly here. The cable glands across the bottom here, they will vary from approximately about a 1/2 inch diameter to about a 1/4 inch diameter. So all we do is we just screw them tighter and tighter and tighter, and the diameter of the cable, the opening gets smaller and smaller, and forms a seal around the wires going into the into our enclosure here. Okay. By the way, these are spring-loaded terminal blocks. So all you have to do is you just take the wire and you shove it straight in, and it locks. And to release the wire, you just take a small slotted screwdriver, press down on the white area here, and the wire comes out. So it's not a screw type terminal block, it's a spring loaded, just push to insert type terminal block. Wiring is super simple, super fast with these types of terminal blocks here. Okay, now configuration of these of the radio. Configuration is accessed. You have to run a terminal program like PuTTY or TerraTerm, and then you plug the USB cable into your computer, and the other end into the USB port on the radio system, and up pops a menu. And the menu is just this sort of basic type of setup here. And towards the end of in Q4 of 2021, we will have integrated this configuration into our device configuration software. That's the same software program that is used by the 415U-E and the 415U-2. But for now, we currently have just this very basic interface. And it's really, really dead simple. To make these two radios communicate like a 415U-2, if you've got its configuration up on your computer, all you do is you just copy the parameters over here. You tell it what modulation this one's using. You tell it how wide your bandwidth is of your frequency, the data rate, the base data rate, etc. All of this information here is going to match all of the information on our device configuration utility software. So configuration is pretty quick, pretty straightforward. In another 6 months or so, we'll have it in a Windows-based format, but all the parameters will be exactly the same. Okay, so now I also took a couple of shots of the cable glands, just to give you an idea as to what it looks like, as sort of from some different angles. Now we've got a heat sink on the back to make sure this guy does not get hot, because it will be mounted outdoors. The temperature range of this guy is -40 to +160 degrees Fahrenheit. And we also have a vortex vent on the side of the unit to allow for thermal expansion. So what will happen is an electrical enclosure like this is sitting outside, and it's a cold day outside. All of a sudden, the clouds clear away, and the sun begins shining on the enclosure. The inside of the enclosure is going to heat up, so you have to allow for that air to vent. So that's we have this Gore-Tex vent on the side of the unit. Keeps moisture out, lets air in and out, lets the unit breathe, as it will need to. Otherwise, you'd end up with some other issues on it here. It could potentially suck in moisture depending on temperatures inside and out and that sort of thing. So we have this vent to prevent that from occurring. We also have a ground screw. It's a threaded connection on the left-hand side. This unit does need to be grounded. It's for a variety of different reasons, but also the antenna connector on the top of the radio system. The surge arrestor for the antenna needs to be grounded. So we have a ground screw on the side of the unit there. Now we have a lightning arrestor screws directly to this connection right here, and that is a type N threaded connection. And we have a new option in our price list of a special lightning arrestor that has a N female and N male connectors. So it threads directly onto this. You have to then weatherproof this connection with electrical tape and the 3M weatherproofing tape, just as you would weatherproof all of your other coaxial cable outdoor connections. So we do have to make sure this is has a good seal around that. Okay, so here we go. I think we've chatted about just about most of the important things here. We've talked about our discrete inputs and outputs. We've talked about our two analog inputs here. We also have added span and zero adjustments to the 4 to 20 milliamp input on this radio system. So that's a new feature. We had not done so in the past, but for a variety of different reasons, they decided to add it to this radio system. So now we can do some calibrations right inside the radio here. Now, if we're transmitting Modbus, we can do it unsigned integer or floating point and that sort of thing. So yeah, very interesting. And you can also read all of the external inputs, and you can see how they're set. You can see what the byte count is over a scale of 0 to 65,000. Format, offset, all that sort of stuff. So it allows you to do a bunch of different things. Now, discrete outputs, they can be discrete or digital, on, off, or we have pulse mode. So we can take a pulse input, and we can produce a pulse output from this radio system. And we also have configurable communications fail timeouts. So, for example, if the digital output was controlling something like a pump, and if you lost radio communications, you did not want that pump to be running, you wanted that pump to shut off, then we can set a fail condition for the digital output. So if radio communications are lost, what do we want the outputs to be doing? Do we want them to fail on? Do we want them to remain at their last known state, or do we want them to fail off? So, and then we have wait times so that we don't trigger these outputs immediately. We wait some period of time to see if the radio can establish communications with the access point once again. Okay. Now we have Modbus smart sensors out there. These are just pressure transmitters, level transmitters that have a 4 to 20 milliamp. That have a Modbus output via RS-485, usually in addition to a 4 to 20. But you can get a lot more diagnostic data via Modbus, so it's becoming quite popular these days. You can pull span, zero, calibration settings, that sort of thing out of these radios, or out of these devices now. So Modbus gives you quite a range of diagnostics here.
Here we go. This kind of shows you the setup menu in your terminal program, how you would configure the whole thing. And of course, we can set the sample time and the warm-up time. So as I mentioned earlier, we could set the unit to have 10 seconds to stabilize, to power up, stabilize the reading. And then once that's finished, then we can go ahead and take a sample and then remove power from the sensor to preserve the battery life. And we can also do a little bit of scaling here as well. And we can have this display in engineering units. So you can enter some scaling here. And instead of showing in byte counts, now we can have this show in engineering units. So something like this, you'd have to take out your calculator and figure out how that translates into milliamps and then convert milliamps into engineering units. We can display the engineering units directly in our configuration utility there. Okay, SDI-12 smart sensors. It's a protocol that's used a lot in environmental applications. So, you know, these weather sensors, this sort of thing. A lot of them use SDI-12 protocol. It's a 3-wire protocol, interfaces serially, and the host automatically scans for sensors and allows configuration of variables and that sort of thing. So very interesting, but floating point types only here. And just like we can with the other inputs, we can have them displayed in engineering units. And here we go. Just kind of shows you what the setup screen looks like for the SDI sensors there. Okay, we also have analog set points in the radios. Now, just to I'm keeping an eye on my watch here, folks. So we are approaching the end of our session today, and just to let you know, we've got just a couple more slides, and then we'll be wrapping things up. For the analog set points, these are triggered off the analog input, and they're designed to fill a tank. So, for example, when the analog value drops down to a low point, maybe 3 or 4 or 5 milliamps, we would want that output to turn on. So what that radio does is it then the radio that has the 4 to 20 milliamp signal wired into it then radios that set point value to a remote radio system that triggers a digital output. That digital output could then be wired to a pump, and that pump could then be filling this water storage tank, for example. So the set point will turn on at your minimum value, whatever you set it to, and then it'll turn off at your maximum value, again, whatever you decide to set this to. So it's designed for filling a tank or filling a liquid storage tank. Okay, now just 2 more slides to go. We have a bunch of internal diagnostic registers. You can log into the radio directly, and you can read what these values are. We also store them in Modbus registers. So you can map this block of registers back to your main SCADA host, and you can be looking at things like the antenna VSWR. Is there a proper 50 ohm load on my antenna for my power amplifier inside? Is the antenna properly matched? Is the radio, the PLL, phase lock loop, working on the transmit and receive ends? We can have alarm of the radio power supply is low, and then a second alarm when it gets even lower. And all sorts of stuff like this, as well as, you know, all kinds of things like internal temperature, radio received signal strength, the solar panel status, et cetera, et cetera. And if any of these alarm conditions occur, there is the OK LED on the outside of the unit. This LED right here will then show as red, and you'll then know that there is some sort of internal fault with the unit here. And one of the things to do is map all of these registers back to the gateway here. So one of the things that we have in our radios is we look at channel utilization to figure out how busy the radio network is. And that lets us figure out, it helps us diagnose any problems we might be having with the radio system. Like, do we need to add IP filtering at the SCADA host? Is a whole bunch of unnecessary radio traffic causing the channel to be utilized much, much higher than normal? So all kinds of diagnostic data is available, and you can store that all on the master radio in your control room at your SCADA master location, so that you can have a great idea as to what's happening with the remote units. Okay, and here we go. Last slide for today. This just shows you the all the diagnostics that we've got inside the radio system. You can read the analog or discrete inputs directly off the radio. You can look at the front panel LEDs to figure out is the unit in alarm condition or not. You can push that button on the front panel to force it to transmit all the values to see if the SCADA system gets the update. We've got firmware updates that we can do here as well. You can save and load these configurations. So you can save all your configurations in case a unit needs to be replaced, and all sorts of different things here. So lots of capabilities in this radio, but ultimately it's a very, very powerful, very effective tool for remote monitoring where there is no infrastructure, where there's no power, there's no electrical enclosures, there's nothing out there. The 415U-1 is ideally designed for that type of application. And that's it. I'm all done for today. I post these webinars every second week, and I wanted to ask, do we have any questions?
Brian, we do have a couple questions. The first one is, when using repeaters, how many repeaters can you use? With a follow-up question of how much bandwidth do you lose from the original signal strength when you use repeaters?
Well, if we use a repeater and we are transmitting serial data, then the bandwidth will drop in half with each repeater that we add. However, if we are just transmitting 4 to 20 milliamp and discrete signals, the actual amount of I/O is literally negligible. For example, a 4 to 20 milliamp signal, 16-bit register, that's only 2 bytes of data. So if we're just transmitting 4 to 20 and discrete signals, as well as some SDI sensor data, there isn't a specified limit on the number of repeaters. But I would say after you get to about 5 or 6 repeaters, you might want to give us a call and just run through the application and make sure we're not pushing things beyond the limits.